Okay, so we started 1.6 development really back after 1.4. So starting in end of June, and a lot of that work, some of that work was the multicolor registration API functionality. So that was rolled into 1.5, but now that's available in the GUI along with a couple of other major projects we've been working on. The biggest project has been re-implementing CNMFE, so we have our own version and now releasing ourselves from any dependencies on the open source packages of Cayman or the MATLAB open source package as well. So we're going to walk through that. So we'll first do a demonstration of multicolor registration. It's pretty straightforward. There's not a lot of different steps, so we should be able to walk through that, look at the outputs, and see how that works. Then we're gonna show you a new line measurement tool that we've made. It's a pretty small feature, but we think it's broadly useful. It's just a way to draw a line and measure it, which comes in handy when you need to enter in parameters like an average cell diameter, for example, and you wanna just be able to measure it on the movie or the image. Then we'll spend a little bit more time going through CNMFE, and Bruno will walk through a little bit of background on there to make sure we're all on the same page for what it is. And then walk through a little bit of a demo so you can see how you interact with it in the GUI. After that, we're going to go through a new additional tools module called deconvolve traces. This is something that is actually also embedded in CNMFE as part of its process. We wanted to pull it out and have it be its own independent tool because this allows you to denoise traces and estimate the underlying spike pattern. And you can do that for either CNMFE cell sets, but you can also now apply that to PCA-ICA cell sets or manual ROI cell sets. So it's hopefully a nice, useful general tool that you can use to denoise and infer spikes on cell set traces. And then finally, we're going to walk through sort of a new PCA-ICA with automatic estimation of ICs. So nothing about the PCA-ICA algorithm itself has changed. We've just added this functionality where instead of having to manually input the number of ICs, you can instead select auto. And then by entering in the average cell diameter, it will make an automatic estimation of that number for you. We validated this against 50 or so data sets and have seen that it generally creates that sort of 20% above the desired number that we get. And so it's not going to work in all circumstances, but we think this is going to be a pretty useful tool for customers. So you don't have to do that, like count the numbers before you try to extract them. Okay. So let's start with multicolor registration. And with that, I'm going to switch right over. There's not really any background here. I think obviously you guys know about NView as the dual color scope. I imagine you've gotten separate training on IDAS about how to collect NView data. Is that true, Shauna? Has that already happened? Awesome. Yeah, because that would have happened for the 1.5 release, right? So you guys know how there's two different modes in IDAS. There's single channel mode, there's multiplex mode. And these are the two different ways you can take dual color movies. And we're going to walk through today an example of deinterleaving a multiplexed movie, as well as registering a static and dynamic cell set for the static dynamic use case of imaging GCamp in green and some static red indicator. Okay, did you follow my screen change there over to IDPS? Wonderful. Okay, so I've just created a project here in IDPS and I've loaded in the data that's in that data.zip folder. So if you guys download that and unzip it, these are just the files that are in there. We're going to start by deinterleaving a multiplexed red and green movie as one of the first steps you might do. We don't actually have on our team an in vivo multiplex movie that we could do. So we just have some synthetic data to show you. So it's not pretty, but this is what it is from the IDAS team. So if you just play it before pre-processing it, you can see that there's two channels here that it's flipping back and forth. And so just like a multiplane movie, we want to deinterleave this movie into its separate channels. We now know from metadata in this movie that this is a dual color movie. So when you click pre-process up here, just like in multiplane movies, it'll say the multiplane movie will be interleaved. Now it says dual color movie will be deinterleaved because it's detected that there are two different color channels in this movie, red and green. Okay, so you can obviously choose your spatial downsampling and temporal downsampling and crop as you normally would. And then as you apply this, I'm not going to keep the raw movies. I'm just going to keep this. And now I'm going to have pre-processed green and pre-processed red. And one thing you'll notice is that they are colored, red and green. And so they're automatically detecting the channel that it's coming from and pseudo-coloring them in red and green for your aesthetic pleasure, basically. So you can, you know, not just refer to the name, but you can also just see with your eyes what the color is. Now, if you decide that you don't want red to be red or green to be green, you don't have to have those colors. You can change them in the preferences panel. So if you go up to here and you go to preferences, one of the things is on video display, you can see the green channel is set to be visualized in green and the red channel is in red, but there's nothing stopping you from changing this to whatever color you want. So if you want to do green as pink and save that, then the green movie will change to pink, and you could have pink and red if you wanted to. Now, one thing to keep in mind is that this is a visualization effect in IDPS, but it doesn't affect how the movie is exported right now. So if you export this movie, it still exports in black and white. I imagine that you guys would like to be able to export the movies and keep that pseudo coloring, so you know it makes your presentations and slides and stuff nicer. That's something we're working on. We're unable to fit it into this release, so this is right now a visual aid while you're in IDPS. Once we are able to export movies with this pseudo coloring, we're also going to open up the ability to pseudo color any movie, not just dual color movies, because you might want to create just from a single channel movie, you might want to pseudo color it as something different for a presentation or graphic. So we don't have that yet because we're waiting until the ability that we can actually export it with the colors overlaid on top of it. So I'll just change this back to something greeny. This is in Scopic screen, a little bit darker. Okay, any questions about that deinterleaving multiplex movies?
I have a quick question.
Yeah.
I'm assuming that everything here is also implemented in the API.
Well, you won't get the pseudo coloring.
Sorry, well, I guess the deinterleaving step is what I'm referring to. I don't know, like, if the plan is to develop the API the same still, or it will kind of be limited moving forward.
Yeah, it's a good. So the plan is still to keep developing the Python API alongside. Bruno, do you have off the top of your head, have we actually implemented this as inside of pre-processing, or is there a separate deinterleave function for dual color movies?
There's a separate function. I believe it's called deinterleave multicolor.
So I think something that came up recently with a customer was the deinterleaving for multiplane imaging. And he made a comment that, you know, in the GUI, when you pre-process, it deinterleaves and pre-process simultaneously.
Yeah.
But in the API, they're kind of separate functions. So if you pre-process the video first, it actually prevents deinterleaving afterwards. So you have to deinterleave first before you pre-process in the API. And I wonder if that's the same for the multicolor, or if there's like some notation in the API to kind of tell people to do one first.
That's a good question. So I think it's the same case here for multicolor movies right now. That's something that we should fix in the future. What happened was with multiplane registration, which happened before this team was here, they did not include that into the pre-processing API. They added it separately. Yeah. So we have to go back now and rethink how to do the pre-processing API function and make sure we can add in that functionality while being backwards compatible, so it doesn't break everybody's API functions when we add in the deinterleaving. So everything else here should be pretty consistent across the API and the GUI, but yes, this pre-processing deinterleaving thing has been awkward since the multiplane days, and we haven't fixed that yet here, so it's still a bit awkward in these multiplex. You have to use the separate functionally, the separate function for deinterleave multicolor movies.
And related to that, is the user guide going to be updated so that the deinterleave for both the multiplane and multicolor are listed in the reference, the API reference?
Oh yeah, definitely. Yeah. Good question. question. But we should make a note. Bruno, can you make a note that we need to change the preprocess API function to deal with deinterleaving both multiplane and dual color movies more elegantly? Thanks. Good question, Jane. Thanks for bringing that up. Anything else before we move on? Okay. So we're going to leave the multiplex movies here, and we're going to move on to 2 movies that were captured in single channel mode. So a single channel green movie, and then a red static movie. I believe it's a movie. No, it's just a static image here. And we're going to use those just to take a look. And then we already have derived red and green cell sets from those that we'll use to demonstrate the multicolor registration. So if you look at the dynamic movie, it's already detected that it's green and displayed it that way. You can see here, it's not a super exciting movie, but it is in vivo. And then we have our red static image here. Okay, so these are this red static image is what you would do your manual ROIs to get the cells. The green cell set, you could run PCI-CA or CNMFE or do manual ROIs if you wanted to get that cell set. And then in the end, we have a green cell set up here that has a bunch of cells. And then we have a red cell set here. So getting to those cell sets is just following the normal IDPS pipeline of processing your dynamic movie with spatial bandpass filtering, DF over F if you're doing PCI-CA. You don't need to do DF over F if you're doing CNMFE. Doing, the selection of good cells and bad cells and sort of all of that classic stuff. So everyone okay about how we get to this red and green cell set? Cool. So then if you want to register these, you'll see that there is a new panel here. We've done a little bit of reorganization in the modules in IDPS. So we made a new panel just for registration. So there's now one thing that's called register cells. And this houses our different registration algorithms that we have now, because we have 3 of them. We have registering across time with longitudinal registration. We have registering across space with multiplane registration. And now we have registering across channel with multicolor registration. So here, multicolor registration is active. You can select it, and it brings up the multicolor registration GUI analysis module, or processing module. So the first thing you're going to do is select data sets from the project tree to add to the multicolor registration processing batch. Now you'll see already here that everything has been grayed out except for cell sets that are known to be dual color. So it has metadata in the cell sets that says this is a green channel, or this is a red channel, and that enables it to be selected for multicolor registration. So I'm going to select my green cell set, come up here, and then I'm going to select my red cell set. And now they're both here. You can see that now that I've selected both cell sets, the apply button has appeared as clickable. So now you could just run it with the default settings if you wanted to, and it would be done. Okay. Let's just take a look at what the different parameters are. So we have 2 different parameters, 2 different threshold parameters, a lower and an upper threshold. This defines the amount of spatial overlap that that 2 cells need to have to either be considered registered or not registered or uncertain. Those are the 3 different possible outcomes of multicolor registration. So this is saying that if you are above 0.7, you could be considered registered. If you're below 0.3, you can be considered separate cells. And if you're between the 2, then we're not quite sure what, it's unclear. And so you're going to get a status of undecided. Okay, and so this allows scientists to change the thresholds in order to be either permissive or restrictive according to the specific hypothesis they want to test. If they want to really make sure that their positive cells are positive and negative cells are negative, then it's good to have those be, the high be high and the low be low, and any uncertain cell you throw out because you're not entirely sure what it is. If you really only care about positive cells, but you don't care if a negative cell is truly negative, then you might raise your lower threshold up, for example, to be more permissive on what cells you're calling negative. So basically it allows you to adjust what your, estimated false positive and false negative rate is. Now, what is that actual false positive and false negative rate? Well, I just got data recently. I think yesterday it was dropped in my inbox from Kevin. That's looking at some ground truth data and seeing how many cells, from a animal that has GFP tagged or mCherry tagged to GCamp. So all cells should be co-localized. What these overlap thresholds should be to recover the true result that this should be 100% overlap. So we're trying to go through that, and hopefully by analyzing that data and meeting over the next week, we'll be able to come up with some more rigorous guidelines for what these thresholds should be. Right now, this 0.3 and 0.7 is not based on a thorough data analysis study. It's just two reasonable values that we've seen work on the test data that we've seen, but they haven't been exhaustively tested.
Hey Shay, I might have lost one part. So how the red cells are extracted using what type of algorithm, or is just manual?
So for the static cell set, the red cell set, it's manual.
Okay, just yeah, okay, I'm good. I think I missed that part. Yeah.
Okay, yeah, no problem. And then for the green cell set, you can choose whatever method you wanted to. So
yeah, sure.
I think in this case it was PCI-ICA, but of course with this new IDPS, it could also be CNMFE, or you could do manual ROIs on the dynamic cell set too if you wanted to.
Okay, so the red is manual basically. That's
the red is manual, yeah.
Okay.
The one thing we don't have an IDPS, which I've been hoping we can get resources for, but it's not totally high priority yet, is a static cell segmentation algorithm for automatic cell segmentation of static images. I think that would really be nice. It would benefit this as well as a couple other things, but hasn't quite made it onto the roadmap yet.
Okay, thanks.
Shay, just one quick question. There's no limit imposed on the e-focus value of the different channels, correct? Or is there?
There's not that I'm aware of. That's an IDPS question to be sure, but I'm pretty sure that you're allowed to either do it at the same focus value if you want, or anything different. Yeah.
Okay.
Yeah, so you could image both the red and green at the exact same e-focus value. Of course, because of chromatic aberrations, that won't be imaging the exact same plane.
Yeah, so I was wondering if IDPS would already take in some metadata and not allow you to co-register cell sets that have been, at least based on the focus value, acquired in completely different planes.
No, but we wouldn't want that, because depending on your lens, you would expect there to be different e-focus values that would actually be imaging the same plane, right?
Yeah.
Do we have any guidelines in the user manual on kind of best practices for drawing the ROIs? Because that can influence your kind of overlap threshold, right?
Yeah, how you draw your ROIs definitely matters. No, as far as I know, there's no guideline on how to do that.
At least, either follow the outline or stay within the cell that you think, something like simple, couple lines like that.
Yeah, that's a really good point, Jane. I think if we don't have something, we should create, and by we, I have no idea who yet, some examples showing good ROI drawings and bad ROI drawings that we could share. Giving people the bad ROIs is always really helpful, just to say, don't do this. But yeah, I think we should put that on, I don't know who will work on it, FSC or on-site support team, but maybe someone to come up with that.
I will say that,
or maybe science team has it. I don't know.
Yeah, maybe science team has it. That'd be
ideal.
Yeah, I will say that what matters, what matters the most is that however you draw the cells is consistent. So, because basically it will affect the threshold that you should use, but as long as you're drawing the cells consistently, even if you're drawing them too big, if you're always drawing them too big, then you should get still consistent results. As long
right,
as
but if you're using ROIs for both green and red, then sure. But if you're doing CNMFE or PCI-ICA and then drawing really terrible ROIs for your red channel, then it's...
So I guess what I'm saying is you're consistent across the cells in your red channel.
Consistently terrible, and then you set your threshold to that.
Exactly.
That makes sense. But yeah, Adani, maybe this is something marketing can take on.
I can check with Kevin and Strishti in some ways what they've been doing, and we can consider adding something in the best practice document.
Yeah.
It is though a bit of it's a little bit of choice involved in how you're drawing, but yeah, we can at least make the aspect.
Yeah, but there's some things that I don't know, I feel like are obviously bad that we could probably guide people against.
Yeah, because I think if you draw, for example, too big and you're including too accidentally or things like that. So.
Okay, awesome. Well, I'll just wait to hear back from you on that.
Yeah, I'll work with Kevin and with Alice's team.
Awesome, thanks.
Right.
Okay, the last thing we're going to talk about here is these outputs. So these are all checked by default. What this is going to do is it's just going to divide your so there's a concept of primary and secondary cell set here, right? When you're registering cell sets, it's kind of there's a reference cell set, and then you're asking which cells in my reference cell set are matched to cells in another cell set. And so the way that that order happens here is that the first cell set that you choose, your green cell set, is your reference cell set, and then after multicolor registration, if you have these checked, then it will just divide that cell set into 3 different new cell sets based on the registration results. So you'll have a matched cell set. These are all green cells that have been matched to red cells. An unmatched cell set. So these are all green cells that have been determined to not colocalize with red according to your thresholds. And then the rest, the uncertain thresholds, that has some degree of overlap, but not enough to be registered and not small enough to be negative, right? And that just really, we just thought that would be a nice simple way for the users to then very quickly get access to all of the registered versus, and then compare it to all of the non-registered cell sets. So I'm going to go ahead and apply and do this. It doesn't take very long, so it's already done. Great. And now what you'll see is that there are a couple of new so for the one I just chose, there's no matched cell set here, which means that there's probably nothing with an overlap of more than 0.7 in those 2 cell sets. So let's try that again and delete everything just to see if we can get all 3. I'll just change that to 0.5 instead of 0.7. Now I have all 3. So now there was obviously some cells that were between 0.5 and 0.7 that got there. So now I have my matched cell set. There was a couple cells that made that questionable quality, and some of these cells that were accepted. Obviously, maybe there could be better quality control going into there. Here's unmatched cells, and here's uncertain cells. But of course, this doesn't tell you anything about like how overlap, like what was the overlap actually looking like and for these cells, right? So what we've also created is some output TIFFs that you can now look at in your project directory to get a sense of what this overlap looked like. So if you go to your project directory, which for here, IDPS1 6 FSC training, let's see. If I just look that up. Here. Okay. So you can say that there's a bunch of stuff just made from the 2 times that I ran that registration. So these 931s are the most recent one. So you can see there's some TIFFs here. There's the matched, non-matched, overlay, uncertain. So the overlay is just the 2 cell maps. It's not very big, is it? Let's open that up to something bigger. Okay, so here is just the overlay of the 2 cell maps, red, green, and yellow. And now we also have separate ones that are specifically the matched ones. So here are all the match cells. Here are the non-match cells. And here are the uncertain cells. So here you can see this is how those 3 cell sets were divided. So there's 6 cells in that matched cell set. There's lots of cells in that unmatched cell set, all of these green cells, and then there's 3 cells in that uncertain cell set. Okay. Now the final thing that you can see here in your project directory, data directory, is some CSV files. Which are down here. So here there's a registration result CSV. So if I open this up, what you'll see is a CSV file, and it has the ID of each of your green cells. So this is your primary cell set. Whatever cell set you collect on first is going to be there. Your matched Jacquard index. So this is how we're computing the spatial overlap between the pairwise cells. And so this is the max amount of overlap. You can think about that as like the fraction of the cell overlap. So 38 would be like 38% overlap, basically. And then this is the max. This is the maximum overlap that COOO green had was with COO red, okay? And it was 0.38. And according to the thresholds that we set, that's above 0.3 and below 0.5. So that was set as uncertain. And so there's no matched ID. And so it's matched to an uncertain ID. And so then when you go to your uncertain cell set, you can see that COOO in your original cell set is now CO in your uncertain ID cell set. Okay, so you can map across the input cell set and the output cell sets. And so then you can go to say a matched ID, the next one, 0.64. So COO1 in green was matched with CO8 in red. And that becomes CO in the matched cell set. Okay, so you can start to see how to map which cells came from your original cell set to then be matched, unmatched, or uncertain, and what that overlap was that set that. Does that make sense?
Hi, Shay. John, I have a quick question.
Yeah.
Probably a stupid question, but so basically, when we use PCI-CA versus CNMFE for the cell identification, I guess we will identify different kind of, PCI-CA components, and for the CNMFE, RY, let's say. Do you think that if we use one or the other, we can get a different overlap that is basically based on the identification per se of the RY? I don't know if I'm clear.
Yeah. So are you saying like PCI-CA and CNMFE are going to produce some different contours, some different footprints, and so then if you run CNMFE versus PCI-CA, you'll probably get different registration results? And I would say, yeah, I think that's likely true. Especially if, for example, your PCI-CA contours are generally smaller than CNMFE, for example, then that's going to affect the distribution of your overlaps, your spatial overlaps, right? Just like how you draw your manual ROIs is also going to affect that. I'm not aware, Bruno, I don't know if you are, or if any of the rest of you are, I'm not aware of a consistent systemic difference between the sizes of PCI-CA contours and CNMFE contours. But I don't doubt that they could be different across different data sets.
Thanks.
I have another question.
Yeah.
So I guess for non-programming people, I don't know if it's easier or worse to kind of change the prefix of because everything is C something something. And if you're just looking at it without the top row, it's hard to distinguish. Like pretty soon you're going to have C1 that kind of corresponds to C5 that corresponds to C2 in a different column. So would it be easy to like name, R1 for the red cells and then like M1 for the matched cell so that there's some distinguishing factor? Because then, C001 could correspond to C08 in the red, but also C0 in the matched. So
Yeah, I see where you're coming from. We could consider that. That would be breaking with convention about how we're naming cells and cell sets.
Anyway, that was a minor point. But the other question I had was how it determines like which cell to match it to. So if you think of like if you have 3 green cells that are next to each other and 2 red cells in that vicinity, you're going to have different iterations of it comparing that 1 red cell to the 3 green cells that are next to it. And so, for example, if you look on this CSV file, in the green column, C015 is matched to C13 in the red, and also C19 is matched to C13 in the red.
No, it's not matched. This is uncertain, and this is yes.
Right, but then the uncertain is because of you changing the threshold, right? So you could have a threshold where they're both.
No, that's a good question. So we've made it so that you cannot register 1 green cell. You can't register multiple cells to 1 cell.
Okay.
So that's a little bit of so great. I'm glad you brought that out. So there are these thresholds that detect you have to be above this to be registered, but in addition to that, it has to be a bidirectional max to be registered. So for the green cell to be registered to the red cell, it's the maximum overlap. You look at the green cell, you look at all the red cells, and this is the cell that had maximum overlap. If you do the same thing with the red cells, you take that cell and you ask, what's the maximum overlap with all the green cells? It has to be the same answer, okay? And if it's the same answer, then we'll call it a match.
Okay.
If it's not.
So if you had 2 green cells and then next to each other, and then the red cell smack dab in the middle of the 2, so that you have, 50% overlap either way. I guess the chances of that happening is pretty low, but that spit out an error.
So something like that, if you can see my screen.
Yeah, like the red is, completely, half and half between the 2, and it's also happens to
so
be.
in that case, if the red has maximum overlap, if the green and red, so in this case, I don't know if you guys can see with my screen sharing as well, but in this case, these 2 would both be maximum with each other, okay? And these 2 would get registered to one another as long as this overlap is above the threshold that you've set, right? And this one, its max overlap would be red, so it would have, say, if this was that C13 cell, this is that C13 being listed in that column, but it's going to be listed as uncertain or unmatched. Even if this was above the threshold, it would still be listed as uncertain because it's already been matched to another cell.
I see.
So this ensures that each red cell can only be matched to 1 green cell.
So what if it was like, I don't know if you can see, like in an extreme example where you have like a complete kind of 50% overlap in that case. So let's say my 2 purple cells are square, and then you have that red square that's in the middle.
I mean, it's just going to be come down to the math, right? If it's exactly the same, then it's going to fail, right?
It's probably going to be
any slight difference, then it's going to go with the maximum one.
Okay.
Good question. Any other questions here? This is it for multicolor registration.
Go ahead.
No, go ahead.
This is probably a question for Danny, but I'm wondering if we are going to have a sample data set for customers that the FSCs can use to demo this, or should they be using this one?
So for multicolor registration, one thing I was also going to point out actually is because we're not releasing in view to the wider community, we don't actually want you to start demoing it. It's actually for users.
Well, I mean, by that, I just mean train. So we have like, I don't remember, like 10 or 11 accounts right now. The FSCs need to train the customers on in view. What data set should they use for that?
I'd just like to point out that with 1.5 and in 1.6, as long as Danny, you tell me not to pull it out, there is an example red and green cell set that's embedded in the installer underneath the examples folder. So if you go to the examples folder in your application, you'll see for multicolor registration, a red and green cell set that you can use as demo data.
Okay, yeah, that's all. And it's like, so then if it's in there, it's customer facing. That's all I just wanted to.
Right. So that's in there currently. Danny, if you don't want it to be in there, let me know. We can take it out. I feel like it's useful for Shauna and your team.
Yeah,
and
it is good to have a sample.
Yeah, it's useful. I'll talk to Alexia. Perhaps the only thing we'll need to think about is when she's putting it in the knowledge base, which is the wider release, where CNMFE will really be the highlight on all the other enabled capability with IDPS 1.6. We can think about what is like something the users can see.
Yeah, I mean, I don't care where it is, just as long as we have one. So I'll just like wait to hear from you on that.
Yeah.
Thank you, guys.
Yeah, and then just one thing to note, it's primarily for training when it comes to multicolor registration for now, because we'll release the IDPS capabilities as well with the full review release, which is slotted for April. Just kind of if you were called into sales conversations, and of course, if the sales conversation is about early access, you're more than like you should demo it.
Okay, so just to clarify, the early access already have access to the 1.6, right?
No, they have 1.5, and then when 1.6 is released is when they will have it, because right, we need to get bug fixes and build the final installer, and then at that point they'll have access to it.
Okay, so the 1.5 is already the multicolor, and now I'm a little bit confused.
It's multicolor in the API.
Okay. Oh, okay, that makes sense. Okay, thanks.
Yeah, so but this is releasing pretty quick. So for anyone who doesn't like using the API and wants the GUI, they're really only waiting about, I don't know, maybe 2 weeks approximately. So
yeah, I mean, that should align when customers start getting data. Yeah, a lot of people just got their systems. And so I think I would prefer FSC's training with this.
Yeah, I agree.
Yeah.
Will it be hard to have the cell maps spit out into the GUI, like, you know, when you generate them?
I was wondering when someone's going to ask me that. Wouldn't that be nice, right? It seems like it should be obvious that you should just be able to view these overlays.
I assume that it's not easy. GUI. That's why it's not there.
So why is that not true? Well, one of the special features of IDPS is that the image visualizer cannot display multiple colors. And so we're a little bit hooped right now.
So
and
it looks the same, like you can't tell. Yeah.
So we just can't. Yeah, we can't visualize the red and blue or sorry, the red, yellow, and what's the other one in here? Green.
Mm-hmm.
So yeah, we can only do one color. We're getting around that with the pseudo colors. But that's just still one color that's being layered on top of that. So we did try to see if we could quickly fix it so we could do multiple colors. We weren't able to do that for this release. It might take a rather substantial restructuring of how we're visualizing stuff in IDPS. So I hope we can do it in the future. I apologize for the inconvenience that we're not able to visualize those images here, but that's the reason why.
But couldn't be there a function that you can just export the two TIFFs and create an overlay as you do it here, but without running the cell registration? You know what I mean?
Yeah, we could offer more general overlays as an additional tool or something. We can discuss that as a feature request for a future release for sure. That's possible. But here we just do that as a function of multicolor registration. Multicolor registration isn't super slow, so it shouldn't be that hard to rerun. But I do agree that it would be nice to have it as an independent module in the future. Totally.
Then I would have a different question. So let's assume that you did the PCA-ICA on one of the channels. Can you then use these counters and apply them to the other channel? So assuming that, or you draw the ROIs manually in the static image, and then you just want to extract only those traces. So without running any analysis, can you directly use those counters?
Yes, you can. You can do apply contours to put the contours of one cell set onto another movie.
Okay.
Okay, the only other result that you get from multicolor registration that I haven't shown you here is the spatial overlap matrix. So this is sort of the raw pairwise spatial overlap. So this gives you an n by m matrix where n is the number of cells in the first cell set and m is the number of cells in the second cell set. And then here is the pairwise overlap. So you can see that, you know, for most cells, they only overlap with one other cell. But there are probably some cases where one column has two. So this cell in this column here, C13, as we noticed in the registration results matrix, overlaps with two cells. So anyways, if the customer wants to just directly access this pairwise spatial overlap matrix, they can do that and do whatever clustering or analysis they want on it. This matrix, this output is not at all affected by the thresholds. The thresholds is what dictates what is, you know, registered or not registered in the registration output CSV, but this is simply computing and displaying the spatial overlap between each pair of cells. Okay, I think we're going to move on to the next thing now, as long as anyone doesn't have any more questions about multicolor registration. All right, Sam, you want to switch it over to you to do the line measurement tool?
Yeah, sure. Okay. Okay, so hi everybody. As Shay mentioned, my name's Sam, and I'm a University of Waterloo engineering intern here at Inscopix this term. I started at the beginning of January with the IDPS team, or the data product team, and I'm working mostly on the IDPS product. And so during the beginning of my term, for the first week or two, I was responsible for implementing a new tool in IDPS, which is going to be used by users to measure lines in movies or like single frame images. So everyone can see my IDPS screen, right?
Yes.
Okay. So as you see here, we have a new tool in the top of the movie toolbar here beside the magnifying glasses, which is the drawing tool. And it's a pretty simple tool. It allows users to be able to just click 2 points on any movie and be able to get the length in pixels in the top. To our understanding, users were kind of using these cursor values in the bottom here before to kind of manually compute these distances, but we just wanted to add a new tool that would be able to let users draw directly on the movies. They can just move them around, draw new lines, and the length in pixels will be updated in the top here. So this can be used in without any modules being selected, or if we have a movie here and we wanted to apply something like PCA, ICA, they can also draw lines, which will be helpful as we see in the end of the presentation during the PCA, ICA part, which can be used to help the user directly input the cell diameter in the future. So yeah, that's about it.
Sorry, this is a really stupid question, but it scales with your spatial downsampling, right?
Yeah, so it's depending on pixels. So it depends, depending how you scale. So if you downsample and you have downsample to a 50 by 50 movie, it'll give you pixels based on that that movie there. Yeah.
And so the only function of this feature is just length in pixels. There's no option to input like a known value.
Not yet, no. So we'd like to, obviously a scale bar is something that we'd like to do in the future to map this back to microns. That's a little bit more work we'd like to work towards. So we just wanted to do this one quickly, but right now this is just pixels.
Yeah, I guess like when I have people ask that questions, it's really to get the micron value. So I think they're still going to need to go into image J, which is fine. I just don't know of anybody that's specifically trying to do like length in pixels.
Well, you need it. So you need it for two functions that we've added for 1.6, which is entering in the average cell diameter.
But it will be in pixels then, not.
Yeah, you need to enter in the parameter asks for the cell diameter in pixels.
I see. Okay. Sorry. Okay, I was thinking about a different function.
Yeah.
Okay.
Is there any function in IDPS that asks for the cell diameter in microns?
No, I'm just thinking about how people want it for like publication purposes, or usually what they want is a scale bar. And so Like one workaround is like if you have you can see the whole lens.
Yeah,
you
you
can
know
use
how.
that. Yeah, and so then you measure it and then enter your known value, and then it converts like all your.
So would that be a satisfying feature for users if they were just able to say this line represents this many microns, and then that would put a scale bar on the movie?
Yeah, because that's happening
we can,
in like ImageJ right now, and so that's what I was thinking of,
okay.
And the requests I've heard about.
Okay, yeah. So I mean, again, we wanted to do this line tool just so you could easily get the parameters you need for CNMFE and PCI-SCA, but I think we're well on our way to just then being able to enter in like a true value and then create a pixel to micron mapping. So
that'd be cool.
We can add that as a feature request for the next release.
Okay, awesome.
Is that easy? I guess if you're taking the whole lens, it would be fine. But if you're taking like the edge of the lens, the chromatic aberrations would influence the actual size there. Right, like I'd imagine the scale would be slightly different.
I think if your lens,
like I'm saying like if you had a tool that if you drew a little line, it would tell you directly what the micron is. Like in reality, it may not be.
I'm thinking of like best case scenario, for example, where you can see the whole lens. You're not worried about the chromatic aberrations underneath. Yeah. You're just measuring the lens. Yeah. That's best case scenario. A lot of times you can't, so it won't work for every lens type.
Yeah.
Shana, Jane, one question. As we're thinking about adding scale bar, we could just simply, though, we know what each pixel value, like the micron of each pixel value, right, from our miniscope. As long as we have, like, we can get that from Mark Charlson.
We can get it, you mean, for a given lens, if they're using integrated base plate, for a given e-focus value.
That's true. The magnification, I forgot about all that.
Yeah, it all changes.
So it all changes, right?
Yeah, we can really get that. If we can make sure, as long as people choose the lens type, we can do the conversion.
It has to be integrated base plate, and then we have to also incorporate the e-focus value. So we have,
so you have to do every e-focus. I mean, if you could do that, that's best case scenario. But I think like one workaround is kind of like estimating the lens size. And like, as long as we say it's an estimation, I think it's okay. Nobody cares on a publication image, but it is something that's requested.
Totally.
Yeah.
But
yeah.
Okay, now that we can
be bigger aim if we can do that, because that's ideal, right? We just automate everything for them. But I think
so that's going to involve then choosing those options and putting that metadata either in IDAS or in IDPS. So I totally agree. I think, we control the optics, so we should be able to automate it. That's going to have to be a cross-team effort with IDAS to try to get that feature off the ground. I think that probably even if we do that, it's still going to be nice to have the feature that Shauna recommended if people are already doing that in ImageJ.
Yes, and there are a lot of people who don't use the integrated lenses, so in some ways we'll still technically need the one Shauna's talking about, because we don't fully control what might.
Just one final point here with the line measurement tool. It's available most places in the app, but not everywhere. So it's available if you're not selected in any module. You can visualize it. We've made sure that you are able to draw lines if you're either in the PCI-SCA or CNMFE modules, because we know that it's when customers are there that they're going to want to quickly get their average cell diameter. Because there are other places in the app that are drawing things on the image and that can create collisions with the line measurement tool, it's not available in if you're clicked in every specific module, it might not be available. So you'll see it gray out. If that's the case, you just need to cancel out of that module and it'll have access to it again. We just did that to simplify our lives a little bit. Otherwise, it was going to get some messy collisions between the line tool and the contours tool, for example. Okay, great. Thanks, Sam. All right, now we're going to move on to CNMFE. So we're going to switch it over to Bruno, who's really led the effort of re-implementing CNMFE over the last 6 months.
Okay, can you guys hear me properly?
Yeah.
Okay, perfect. Just that being... Okay, so yeah, so for those of you that I haven't met, so my name is Bruno and I've been working with Shay for about 9 months, I think now, on the data product team. And so I've been working on developing new features in IDPS. And one of the big projects that we've been working on in the past 6 months was the re-implementation of CNMFE. So earlier today, you guys were asking about whether 1.6 would involve changes in the API or whether there would be any changes there. And CNMFE is one place where everything is going to be different as of 1.6. So prior to 1.6, you could only run CNMFE using the 2 APIs that were available with IDPS.
Just to be clear, when he says everything, he means everything about CNMFE, not about everything else.
So prior to 1.6, you were probably familiar with using CNMFE through the Python or the MATLAB API. And one thing that might have been annoying to you is that depending on which of those 2 programming languages you were using, like depending on which version of CNMFE you were using, you were getting a different output. And also the output units that you were getting were probably different. You were probably getting traces on different scales. And so this is one of the questions that we've also received a lot. What are the output units of CNMFE? And why am I getting different results when I'm using these 2 different implementations? And so with this re-implementation, one of the things that we did is that we've only made one implementation of CNMFE that's consistent across the board. So whether you use it in the application interface or whether you use the Python API or the MATLAB API, now you're going to get the same output, no matter how you use it. And so here I call it the story of a button. And the reason for that is, despite the fact that this is actually a huge feature under the hood, it ultimately boils down to a single button in the graphical user interface. So this new button will be available from the Identify Cells menu. So when you click it, you'll have this new method for identifying cells called CNMFE. And it comes with a number of tunable parameters that you can tune depending on the movie that you're trying to analyze and the kind of output that you're trying to get. And the output that you're going to be getting from CNMFE is essentially the same type of output as PCICA, so a cell set, where you're getting a set of footprints, spatial footprints, and also a set of temporal traces. And so this is what I'm showing at the bottom. And one noticeable difference with between PCICA and CNMFE in this case, you'll notice that the footprints are a lot cleaner with CNMFE. So with PCICA, you'll see sometimes there's a lot of, it looks like almost like an image. So you have a lot of different pixel values across the image, but with CNMFE, you're going to get much cleaner footprints. You're going to get white or gray pixels for the cell, and then black everywhere else. And also the temporal traces will be better denoised, and that's because one of the properties of CNMFE is that it really models the background in a way that's better than previous algorithms that were used. And so this is what I'm showing on the right. So one of the traces for CNMFE, and underneath these are just the 2 events that were identified from that trace. So before I go into more details about what CNMFE is and how it actually works and how you can really control how it works using IDPS, just want to briefly talk about the highlights of this project, because I think there's a number of things that were unique to this project that are interesting to mention. So one of them is, so this new team that Shay started in Vancouver is relatively new. So it only started back in May, I believe, when Braden and I joined. And so this is really the first version of IDPS. So one of the big features that we own from beginning to end, the development of CNMFE. It took about 6 months to re-implement this algorithm. So it's really a big algorithm, despite the fact that it might look simple from the user's perspective. So there's been 3 full-time developers, so always two developers at the same time, so myself and a co-op. And there's also been many contributions from Shay and Braden. In total, there's about 17,000 lines of code, and I realized that it might be hard to determine whether that's big or not. And I didn't have a chance to compare that number of lines with the rest of the features in IDPS, but my guess is that it's probably just as big as all the other features in IDPS combined. So it's really a big module that we've added. And the reason for that is because CNMFE relies on many other algorithms to do different parts of it. And so that forced us to re-implement a lot of different algorithms that exist out there. It's also the first time in IDPS that we're doing things in parallel. So prior to CNMFE, everything was kind of done sequentially. So if you had a movie and you were running PCA/ICA, for example, it would take one frame, process it, take the next frame, process it. So it'll go through all the frames one at a time. But with CNMFE, that's not entirely possible because of the way the algorithm works. And also because of the fact that it's very computationally expensive. If we were not doing things in parallel, it would really take forever to run CNMFE. And the last thing is, yeah, it's the algorithm with the largest number of tunable parameters in IDPS. And there's, I think, a total of 13 parameters that we're exposing to the user. And there's also a number of other parameters that we can tune in the background or that are also exposed in Cayman and the other MATLAB implementation. And there's a lot of those parameters that most users are probably not even aware of, so they're automatically set in the background. And in this implementation, we've tried to make it really clear what each parameter is doing and how it will affect your output. Okay, so maybe just to make sure we're all on the same page, I just want to mention what CNMFE stands for. And
hey, Bruno, sorry, yep. Before you go on, I just have hopefully a quick question. First, thank you for that overview. It's nice to get the historical perspective and understand like what it takes for you guys to do this. And then my question is related to like the comment you made about it being computationally expensive. So yesterday I was on a call with a customer and he gave some feedback that our computer spec recommendations for PCA/ICA and running it through IDPS are not great and they actually don't work well. So are we going to need to change that? And do we expect that with CNMFE to be even more computationally heavy, or does this parallel system you guys set up account for that?
Yeah, so I can address one part of that question, and then I think Shay will probably address the other one. So one, like the question about whether it's more expensive than PCI/CA, well, it definitely is. And that's just even despite the fact that we're doing things in parallel, it will consume more resources on your computer. And I think the current recommendation in the IDPS user guide is to have something like 64 gigabytes of RAM in order to run CNMFE. And that's the kind of system that we've been testing our implementation with on data sets that were about that big, like 60 gigabytes. We tried one of those. And well, yeah, I don't know if you wanted to address the other part, Shay.
I can jump in. So a couple things. One is when you said our recommendation is bad, was he saying that he needed more computational power than we had recommended?
Yeah. So he said he ended up having to buy another computer.
Right.
So, I mean, that was the first time I've heard it, but I mean, knowing that and the same customer wants to use CNMFE in the GUI, because that was one of his complaints, just want to make sure like it'll work for his current setup and he doesn't.
Yeah, so it's always going to depend. It's always going to depend on the size of the data, right? So
right.
So it's going to be on how big each individual movie is and how they're pre-processing it in time and space. So there's definitely lots of recommendations we can give for trying to decrease that data size footprint to make it go faster. Another thing that we've done in our implementation of CNMFE is offer some different processing modes, which Bruno is going to go over in a little bit. And that allows the user to select a mode that will be most appropriate for the amount of computational power they have and how big their data is.
Okay,
so basically there's always going to be a trade-off between how much memory you're consuming and how fast it is. So if you have lots of memory to burn, then you can do CNMFE faster. If you don't have lots of RAM, then we offer a mode that will consume less memory, but will be slower. And so that will allow users that have less computational power to still use CNMFE, but of course, the drawback is that it will be slower for them.
Okay, that sounds like it'll be really helpful. Thank you.
No problem.
Okay. Yeah, so just to make sure that everybody is aware of what CNMFE is and what it stands for. So it's, like I was saying, it's a new algorithm to identify the location and temporal activity of cells. And here I've broken down the acronym so that you know what it stands for. And really the core concept in CNMFE is this idea of a matrix factorization. And what that means is essentially with the formula that where I'm using plain English. So movie is equal to spatial times temporal plus background plus noise. So what that means is the idea in CNMFE is that you want to be able to reconstruct the neural activity in your movie by multiplying two matrices, one that would encode the spatial information, so the location of all your cells, and then one that would encode all the temporal information, so the activity of all your cells over time. And the idea is that when you're multiplying those two things together, you're recreating the neural activity that you're observing in the movie. And then, of course, this reconstruction is not perfect. There's always some background fluctuation. And whatever you can't explain with this model is sort of included in the noise. And this is depicted in the pictures at the bottom of the slide, where I'm showing a frame from a movie and then decomposing it on the right into the three different components that I was just mentioning. So neural activity, background, and the residuals, which is the noise. And then one other thing that's really important about this algorithm is that it's constrained in many different ways. So because we know the shape or what the temporal activity of the neurons should look like, we can apply a model to the calcium dynamics to make the identification of cells more reliable and better. We also apply some constraints on the shape of the footprints, so the shape of the cells. So we enforce that cells be a single location, so a single region of interest, as opposed to having multiple and scattered pixels that combined would form a footprint. So that wouldn't make sense biologically. So we're really enforcing a single region of interest. We're also enforcing a circular shape in this algorithm. And yeah, the non-negative part just means that we don't allow net values to be negative, because that wouldn't make sense. So here's an overview of our entire implementation of CNMFE, where you start with your input movie, and then it goes through a sequence of 18 modules. And then at the end, it spits out the cell set, so the set of spatial footprints and temporal activity. And then the colors here simply represent different parts of the algorithms that are repeated multiple times during processing. So you'll see, for example, update spatial components in red. And that's because CNMFE is, that might be confusing at first, but I'll clarify. So it's it's basically an algorithm that will attempt to solve a non-convex optimization problem. So the optimization that I'm talking about is you're trying to minimize the difference between your original movie and the movie that you're reconstructing using your model. And so when you're minimizing that difference, it means that your reconstruction is really good. And then the non-convex part of this problem is the fact that depending on, so basically the non-convex means that there's different reconstructions that might give you the same difference between the original movie and your reconstruction. And that's largely dependent on how you initialize your components in the movie. So depending on what you call a cell initially, you might end up with a slightly different result. And that's because the algorithm is also an iterative algorithm. So it starts by, you can think of it as a guess. It takes a best guess as to where the cells might be in the movie. And then it basically iteratively, I can't say that word, but there's a number of iterations where the algorithm improves those estimations. So it improves the footprints, and it also improves the temporal traces. And at the end, you get an estimation of the neural activity that's much better than what you started with.
Hey, Bruno,
yeah.
Sorry to interrupt, but I was just wondering if some of those slides could be customer facing, because we have some educational tools as FSCs, and including some PPT that we usually use for education. And I think those are really, really good. So it might be great if we could show during our training.
So I think so this diagram and most of what we're going to show you today is actually in the IDPS manual.
Okay, awesome. Thank you, because this is really, really good and helpful to explain difficult concepts.
Now, not to say that we can't make these slides available to you guys, but I think most of the figures you see today will be in the CNMFE section of the new manual. Yeah. Okay.
Yeah, we can crop them and put in our presentation. Yeah.
And there's actually also even more details in the user manual for the release of 1.6. So I'm not going to go into each individual module today, but there is information about how each module works in the user guide. So I have this diagram, and then I basically go through all 18 modules so that you know exactly what's going on.
Awesome, thanks.
Yeah, so also the parts that are colored here also refer to the core of the CNMFE algorithm that's kind of common to Cayman, the Python open source implementation of CNMFE, and OR implementation. And then the modules in gray, so modules 1 and 2, as well as 17 and 18, these are slightly different than the open source implementation. So this is just our way of optimizing how we're dividing the work for CNMFE and how we're recombining the results at the end. And I'll go back to this idea of division of labor in a second. But that's essentially the overview of the algorithm. So this is what I was saying before. So it initializes your neurons, it takes a best guess, and then it goes through a sequence of repeated modules, like estimating the background, refining the spatial footprints, refining the temporal traces, so that you get better estimates of where the neurons are at the end. Okay, so let's just talk about the input parameters. And at the end, I'll just give you a little demo in the IDPS so that we can actually see it in action. But these are screenshots taken from the user interface in IDPS. So the first box where you see average cell diameter and trace output units, these are in the regular panel. So they're displayed to the user by default. And then everything at the bottom next to advanced, you would have to click the advanced button in order for them to display. And so the two parameters that are
just one thing on that also corresponds to what we think are, the users need to input the average cell diameter, because we're not going to guess that for them, and they need to tell us what kind of output units they want, and we've tried to make those interpretable, which we'll talk to you guys in a bit and explain what those output units are. The advanced is, we've given these are good default parameters, and they match some of the default parameters of Cayman as well. And we're also doing a pretty good job of inferring parameters where we can. So we're defaulting things as auto, and we think we can do a good job of actually estimating these parameters from the data. So in a lot of cases, the only thing that the user should worry about at the very beginning is just the average cell diameter, and then click go. Now, when they want to tune those results and start to introduce subtle differences to pick up more cells or fewer cells, that's where you can start to mess with the advanced settings, but it's not something that you necessarily have to do all the time.
Yep. So yeah, I'll have another slide to really clarify what we mean by trace output units. But basically what this option allows you to do is what Shay was saying. It really gives you more control on what the Y units are going to be for the output of your CNMFE. So this is unlike other open source implementations where you only get one output units, which most people often don't even know what they are. And and when you look at the documentation that they provide, it's also not always super intuitive to understand what they mean and how you can compare cells together. So with this, I think we're making it a lot clearer for users. And then the reason also we're putting average cell diameter is because we think it's one of the most important parameters that you have to specify in our implementation of CNMFE. And that's because it guides the algorithm in taking this initial estimation of where the cells might be. And also because some of the other parameters that you see at the bottom are marked auto for automated or automatic. Yeah, they're estimated from that cell diameter. So if you don't specify a good cell diameter, it will have a significant impact on the quality of your output. So that's why we're also offering this line measurement tool to help you more appropriately measure a cell diameter. And then here I'm just coloring the different parameters, and I can share that slide with you guys also, just to show you which of the parameters refer to which modules in the diagram above. So if you see, for example, the orange diagram, the orange module, the initialization, so the three parameters that are highlighted in orange would have an effect on this module, would have an effect on the initialization. So by initialization, we just mean this initial guess of where the neurons might be. And there's more details about how that works exactly in the user guide.
As Bruno mentioned, this initialized, because it's a non-convex problem, which basically means that there are different optimal solutions depending on your initial set of parameters. The initialization module is really important, right? So when you get bad results, usually the first thing to do is going to be to change your average cell diameter to see if you have a bad cell diameter estimation. But the next thing is to start to play with the parameters that are in the initialization module. So here, that's the min pixel correlation, the min peak to noise ratio, and the Gaussian filter width. Because the key to better CNMFE outputs is usually trying to get a better initialization result. And then the CNMFE algorithm can iteratively improve on that for your outputs.
Yeah, and then the last three parameters on the far right, where it says processing mode, patch size, and patch overlap. I have the next two slides where I'm going to go into more details on what they are and how you can use them. But this is essentially where we're doing this division of labor. How can we divide the work for CNMFE so that you can be more efficient in terms of either time or memory consumption? So if you want the analysis to run faster, or if you want it to consume less memory and you care less about how long it's going to take, that's kind of those are the parameters that you would need to play with. Okay, so maybe I'll just talk about the output units before I talk about this division of labors. So the output units are what I mean by output units are these Y units that you see in IDPS. So currently there's nothing that tells you what they mean, whether you're looking at them in IDPS or whether you're extracting them to a CSV file. And people are often confused about that. And so one way that we made it really clear is this drop-down menu that you have when you're running CNMFE allows you to specify the output units that you want to use. And we're currently offering 3 different possibilities. The default is the one in the middle, DF over noise. So maybe just starting from the top. So the first output units that you can specify is something called DF. And that refers to the fact that we're outputting traces that are roughly, that we're trying to output traces that are on the same scale as the original movie. So, and the way that it's doing that, oh yeah, go ahead, Shay.
I was just gonna say, so DF here, where, you know, the movie that you have, the raw movie has these pixel intensities, right, that are varying, and DF is really, this output unit is really gonna be on the same scale as those intensities. So when you're talking about, if you see on your DF scale that, you know, it goes from 0 to 5, that's going to correspond to that pixel in that original movie changing by 5 units in that neuron. And of course, that's background subtracted, right? So it's not the raw pixel movie it was, but it's with the background subtracted from it. So it's the DF, not just the F, right? The change in fluorescence. So that should map back to the original units of the data of the movie.
Yeah. So that's the first option that we're offering. So DF. And then the second option is this thing called DF over noise. So that's slightly different than, well, so maybe I could just define it. So basically you're taking the temporal traces and you're dividing them by the amount of noise that you estimated in each of the temporal trace, so for each of the neuron. And that allows you to compare different neurons together, regardless of how much noise affected their temporal activity. So even if they have different levels of noise, you can still compare them because you account for the noise in that output unit. And it's very similar to a z-score in the sense that when you calculate, some people might want to take the temporal activity and z-score them. And the DF over noise is essentially the same thing, with the exception that instead of dividing by the standard deviation, we're dividing by the amount of noise, which is more robust to the variance in the temporal activity than the standard deviation. So it's not affected as much by outliers as the standard deviation would be.
Well, so the problem with just taking a z-score of your temporal trace is that the z-score is going to be affected by the number of spikes in the trace. And of course, that doesn't make any sense, right? Because you want the noise estimation to not include the actual spikes themselves. So our noise estimation here, we do a filtering step we do a Fourier transform, in fact, to basically filter out those spikes so we can do a noise estimation, which is basically equal to taking the standard deviation of the trace, but only in places where the neuron is not firing an action potential or not, you don't see a calcium event. And that's then the estimation of the noise. And so then you get a more robust Z-score-like unit.
And then the last output units that we're offering is called scaled DF. So this is probably the output units that you guys are most familiar with. So it matches the output units that you're getting from the Python open source implementation called Cayman, so the Cayman package. So it represents the average fluorescence of all the pixels in your cell. And we're calling it a scale DF just because we're basically taking the average of different pixels in the ROIs that have different brightness, but overall they share the same temporal profile.
So the scale DF is probably the hardest to interpret, I think, of the three. And I think that's probably why it's been hard to interpret from Cayman as well. We wanted to offer it here because we want the users to have the option to match Cayman outputs exactly so they can get the same units, just so they can see that we can provide the same thing. But they're harder to interpret. The scale DF refers to the fact that you're normalizing to the spatial footprints, but it's not totally intuitive then how you compare the traces to each other. So we think that DF over noise and DF will be the more interpretable units, and that scale DF will be used when the users want to be able to directly compare the results to Cayman.
I have a kind of general analysis question where you can imagine that a lot of customers are imaging, let's say, a 10-minute session, but there is some stimulus that comes maybe, let's say, in the middle, 5 minutes in, and really what they're looking at is the activity maybe 1 minute prior to that stimulus and 1 minute after. So when you're analyzing the whole video, you're getting a lot of other activity that may not be related to what you're interested in. And, you know, like Shay was saying, how a Z-score calculates all of the spikes throughout the entire movie. So how important is it to kind of crop the image before all of processing, or is it okay if, you know, they're processing everything and then after they've selected ROIs and done all of these analyses to then just take a snippet of that processed data?
That's a great question. So the answer is that it's not. So when you say crop the movie here, I'm assuming you mean in time then. So you're saying, oh, I just want to crop it to right exactly when the stimulus happens.
Yeah, like the plus or minus 1 minute.
And I would really differentiate the trying to estimate the activity of the neuron from trying to compare across a stimulus, because basically the more information that CNMFE has, the more time points it has for the pixels, the better it's going to be at really estimating where that neuron was and what activity it was over time. So it's better to keep the whole movie there within reason, right? I mean, if it's hours and hours, but if it's 10 minutes and you care about the middle 2 minutes, you should for sure do CNMFE on the whole 10 minutes. And then afterwards, crop the time points that you care about out to analyze them.
So then related to that, is there a kind of minimum frames that you would need for CNMFE to work properly?
I mean, it depends on your frame rate and your activity, but
like if you had a 30-second recording, will that be fine, or does it need to be at least 5 minutes? You know,
if you have a 30-second recording at a high frame rate and
like
your
10 to
cell's
20,
active, then
I guess most people probably image between 10 to 20 hertz. So yeah.
So you can always identify regardless of the number of frames. So even if you have 30 seconds, you'll be able to run CNMFE. It's just that if you have more frames, it's more likely to give you a better output.
Okay.
Yeah. It's just gonna, it's gonna still do the job. It just might be worse.
Yeah, and also if some neurons are only active later than 30 seconds, then you wouldn't identify them because it's also looking for active regions in your field of view.
Sure. Thank you.
Okay, so maybe just another note on the output units. So just to make it clear where you can get more information about your output units is when you're right-clicking a cell set in IDPS. So we've added a couple of new metadata fields. And one of them is this thing called cell identification method. And so that will keep track of what algorithm you used to identify your cells. So in this case, we use CNMFE. And then underneath that, you'll see traced units. So we're keeping track of what the Y units are. So if you ever forget what output units did I use for this algorithm or for this cell set, you can always look at the metadata and get that information. Okay. So one important thing that we were talking about earlier is this idea that we can control how we want to divide up the work when CNMFE is running, so that it either consumes less memory or takes less time to run the entire algorithm. And so starting with the top branch here, so we're offering 3 different processing modes. One of them is called all-in-memory. And what that means is that we're essentially taking the entire movie and fitting it into in the memory of your computer. And so that option, you can already tell just by what I just said, that you would need a lot of RAM, like a lot of memory on your computer if you wanted to use it, because you need at least enough RAM to fit the movie, but you also need enough memory to allow for all the extra memory that the algorithm will use while it's processing the movie.
So think about this, we're dividing the movie. We're trying to recreate the movie by estimating the neural signal and the background and the noise. So you start with 1 movie, but now we have 3 movies, neural signal, background, and noise. So right there is like a rough 3x multiplication of the amount of memory that you're going to need in RAM. So if you have a 5 GB movie you're trying to read in, you don't need 5 GB of RAM for all in memory. You're going to need more like 15 GB of RAM for all in memory. Roughly.
So, yeah. I think the only case where you might be interested in using this mode is when you have a lot of memory on your computer, like she was saying, at least 3 times the size of your movie. And also if you're really worried about the fact that if you were to divide the field of view to do processing in parallel or whatever, when you're recombining these things together, if you're worried about the patch, the border effects, then you might want to go for that mode.
But we do I think we handle the borders pretty well when we're merging them. So there should be no particular fear about dividing your movie up into patches.
So that's the first mode, so all in memory. The other 2 modes revolve around this idea of dividing the field of view into smaller spatially distinct areas that can overlap. And so here I'm giving an example where we're splitting the movie into 4 different movies. And then we have 2 ways of processing those, what we refer to as patches. One is sequential, which is exactly what it sounds like. You're processing each portion of the movie one after the other. And the advantage of doing that is that you're only consuming as much memory as you need for a single patch at any given time. So if you had a very limited amount of memory, that's definitely the mode that you would want to use, because that's the one that would use the minimum amount of memory. And the smaller your patch, the smaller the amount of memory you'll be consuming.
It'll also be the slowest.
Yeah, that's what I was going to say. So this one, because it's doing things sequentially, it's also going to take more time than the other approaches. So that's the trade-off here. You're going to consume less memory, but it's going to take more time.
Do you have an estimation for the different time? Something that we can tell customers?
Yeah, we've done benchmarking of some different modes. We don't have that in our presentation here, but we're putting that together in some like a white paper basically for CNMFE that we'll send out to you guys in the next couple of weeks.
Thanks.
And then at the bottom, you have what we call the parallel patch mode, which would be the fastest of all, but it would also consume a significant amount of memory. So you would need at least as much memory as the 4 patches that you're trying to process. So the good news is you can always control the number of patches that you'll be processing in parallel at any given time. So here I'm splitting the field of view into 4 different areas, but you can imagine that if you had a larger movie, you might split it into 9 different areas. And if you were to process all 9 patches at the same time, then there would be no difference with using all in memory. You would just be processing the entire movie. So the idea with parallel patches is that you're processing multiple parts of the movie, but not the entire movie. And then you process those small chunks in parallel, and that makes overall the algorithm a lot faster.
So that's our suggested mode, parallel patch mode, and that's the default.
Is it the goal then to ultimately at the end of processing have processed every piece of the movie.
That's
It's
right.
just, you might get some data faster than doing the all-in memory. But
Yeah,
I guess what's the benefit of doing parallel patches if in the end you still have to process the entire movie?
Well, but you don't process it all in memory at the same time. So it's still consuming less memory than all in memory.
I see. So then you can, like, let's say process half of the movie and maybe see some results before you process the other half?
No, it's not gonna, you're not gonna see any
Okay.
results.
Okay.
It's just gonna be on the inside how it's processing it. But all three of these processing modes will still just run to completion. At the end, you'll see one cell set that pops out.
Okay.
Yeah, so it gives you more control on the amount of memory you're consuming. So you can specify the number of patches being processed at any given time. But at the end, all these three different processing modes will all generate a cell set as you would expect. So you're going to get a set of spatial footprints, a set of temporal traces. There may be small, slight differences between the all-in memory, the output that you're getting with all-in memory mode and the patch mode. And that's also something that's observed in the open source implementations. And that's because of the way that we're combining the results from these different patches at the end. So we've run some tests to see if they were significantly different, and in our implementation, it's quite consistent. So you're not going to see major differences. It might just be a few cells. You might get a few extra cells with one implementation versus the other.
We actually feel like this is a place that we've made a bit of an improvement over the Cayman implementation. It seems like our implementation is more robust to delivering similar results across different processing modules, whereas CNMFE, depending on if you use parallel patch or all in memory mode, you can get a large different number of cells.
Yeah. So that's definitely an improvement we've made. So our implementation is more, the output will be more consistent regardless of the mode that you're using. Whereas if you were to use the open source implementations and use different processing modes, it leads to more different outputs.
I have a question about the RI or this patch. Is it possible to preview the CMFE using RI and then maybe a small chunk of the movie instead of the whole movie? Just to have a testing the initialization parameters.
So I think
that's a good idea. No, it's not currently possible with our implementation, but I like that as a feature request that you could submit for future, just to run CNMFE on one of the patches, for example.
Yeah, I mean, the only way you could do that currently would be to manually use the pre-processing module to crop a small patch of the movie.
You could
process it using CNMFE, and then you'll see what the output looks like.
That's true. So you could just crop whatever you want, a small part of the movie, and then pass that in as all in memory, and then you would get effectively the same thing.
Yeah, I think that's what I'm doing now, just using a trim function, trim movie, and to get a small number of frame number, and also downsample the movie a lot, just to get some initial.
So downsample the movie is great, and we recommend doing that in general. But of course, if you're trying to tune your parameters, then you don't want to tune your parameters on something that's downsampled differently than what you want to run the whole thing on.
Okay.
Thanks.
Yeah. So
question. So what is about the background? So how is it estimated? It's using the entire video or then a single batch?
Yeah, it's using the background is estimated for every individual patch. And then at the end, we're recombining the patches together to form the overall background, just like reforming the overall footprints and neural activity across the field of view.
And actually, there's also individual background estimated for each neuron as well.
Yeah, I mean, it goes even further. It identifies the background for every pixel.
Every pixel, yeah, that's true.
And then we also have it for every neuron afterwards when we're like combining them into neurons. So
the background estimation is pretty cool, and we have some more information about that in the manual. But I think for now, I'm going to get Bruno to speed up because we still got a few more things to go through, and we're coming up against the hour here pretty soon. So maybe Bruno, if I could get you to.
Okay. Yep. So the two parameters for the patch mode that you'll see in the interface are patch size, which just refers to the side length of a square area that you're cropping out of the movie. So all the patches will have the same size, and they'll just be, you can imagine that you'll just be sliding that little square across the field of view until you cover the entire field of view. And then patch overlap is the amount of overlap that you're allowing between adjacent patches. And so you could imagine you would want to make sure that the overlap is at least as large as half the neuron or the neuron, because if it wasn't like directly on the dividing line, you would still want to be able to identify. And so this is also how you can control the amount of memory you're consuming. So if you increase the patch size or decrease the patch size, it will help you control the amount of memory. I think that's it. So I'll just show you quickly in IDPS what it looks like, and then I'll hand it over to Shay for the other features.
You still have the comparison.
Oh, shoot. Okay.
Cool.
How do I share this thing? New screen share.
If you just shared that individual window, you're going to have to stop screen sharing and try again. Otherwise, if you shared your entire screen, you should be able to just switch to your IDPS window.
Okay, you guys see
you're good. Yeah, I see it.
So for CNMFE, one of the differences with PCICA is that you don't need to run the DF over F. So you basically process your movie the same way you would normally. So you pre-process it, spatial bandpass, and motion correct it. But then you don't need to run DF over F. And this recommended workflow is also detailed in the user guide. So to run CNMFE, you just go under Identify Cells, CNMFE, and then you have exactly all these parameters that I was talking about earlier. And then just to run it with the default parameter to show you what it looks like. So it takes a little bit more, actually a lot more time than PCICA, depending on the size of your movie. So if you have a very long movie, it will take significantly longer than PCICA.
Bruno, just a quick question. So I had a chance to play a little bit with CNMFE, and I noticed that you can basically use a DF over F as an input for CNMFE, as well as use, for example, a motion corrected movie as an input for PCICA with this version.
There's nothing stopping you from doing it. It's just a recommended workflow.
Okay. Okay.
Yeah.
Okay.
So CNMFE will work with any movie that you're going to feed in. It's just that in order to get optimal results, I recommend using motion correction. I think somebody's baby.
I will ask those to be.
Okay, so this is the output that you're getting with CNMFE. So same as before with PCICA, where you're getting a spatial footprint and a temporal trace, but you see that they're much cleaner.
Hey Giorgio, could you mute yourself?
Okay, thank you. Okay, so that's essentially how you would run CNMFE in IDPS. And now just to try to run through that section quickly, Shay, to give you enough time for the other features. So the last thing we did is can you guys see my slides here?
Yeah.
Okay, the last thing we did is we compared our results to Cayman just to see if what we were doing, what the output that we were getting with our implementation of CNMFE was comparable to Cayman. And the reason we compared to Cayman is because that's the implementation that we followed to implement it in IDPS. So Cayman is in Python, or implementation is in C++, but they follow the same logic under the hood. So this is a sample data set that we used to compare the output from the two implementation. And what we're showing here are called cell maps. So on the far left, you have the input movie. And next to that, you have the cell map that we got from Cayman. So a cell map is just an overlay of all the individual spatial footprints into a single image. So that gives you an idea of all the cells that were identified using this algorithm. And one thing to specify, you'll see there's a lot of cells along the blood vessels, and that's because these cells have not been filtered, and they're just a raw output from CNMFE. So all the cells that came out of it.
So there's been no component evaluation done yet. So we're just comparing the raw outputs of us and Cayman right now.
And then next to that, we have the output from IDPS, which you can see looks fairly similar. And just to visually confirm that, we generated an overlay of the two images in the middle, so Cayman and IDPS. And then the two colors, so green is Cayman and purple is IDPS. And so you can see that they're overall very similar, although there are slight differences in some of the spatial footprints. but nothing major. And then, so one thing that we did in order to more accurately compare these two cell sets, the cell sets that we were getting with Cayman versus the cell sets we were getting with IDPS, is we came up with a similarity metric that would allow us to compare two things: compare whether the footprints, the spatial footprints, were similar, and also whether the temporal activity of those two neurons were similar. So if you look at the first three graphs here, see you have two spatial footprints that look quite similar. So one of them is from IDPS, the other one is from Cayman. And so what we do is we calculate the correlation between those two. And then we also calculate the correlation between the temporal activity obtained in Cayman versus the temporal activity obtained in IDPS. So we have a temporal correlation and spatial correlation, and then we average those two together in order to get this metric that we call spatial temporal correlation, which gives us an idea of whether the cells identified in IDPS and Cayman are similar, both spatially and temporally. And then at the bottom, you have an example where this spatial temporal correlation was lower. So it's only 0.67, but you can still see when you look at the spatial footprints that they were trying to identify the same cell. So it's roughly the same area in the field of view, although the two algorithms identified slightly different temporal traces, with the IDPS trace perhaps looking more like neuronal activity than the one that we got with Cayman. And then the graph on the right of this slide is the way that we're evaluating similarity across overall, like across all cells in the recording. So you can imagine, so this spatial temporal correlation, so we get different numbers for all pairs of cells, but it's very hard to say what number you should use in order to say, yes, these are the same cells, or no, these are not the same cells. So you could use like different thresholds. And so what we did is, instead of using an arbitrarily chosen threshold, is we varied the threshold from 0 to 1 in order to see how many cells, like what proportion of cells would be matched between Cayman and IDPS, regardless of the threshold that you're using, or for all values of the threshold that you could use. And so that's the graph that's shown on the right. And it looks like the kind of graph that you would want to see. So you would want to see a curve that's really towards the corner, where regardless of the threshold that you're using, you're getting a match between all the cells in the two cell sets. And
so then very, very practically here, an area under the curve of 1 means that everything was exactly spatially and temporally identical. So that would be like a perfect match if you just took the same cell set and compared it to each other.
Yeah, so this is the metric that we've been using to compare two cell sets together, the area under that curve. And so what we did then is we compared the output from Cayman and IDPS for, here we have like 7 or 8 different cell sets. 8 different recordings, sorry, that were identified across various brain regions. So we wanted to make sure that regardless of the number of cells that were imaging or the different brain regions that we're imaging, we're getting an output that's quite similar to what Cayman is getting. And if you look at the last column, this AUC area under the curve, so that tells us how similar the two cell sets were. So the output from Cayman versus the output from IDPS. And you can see that overall, they're very in line with each other. Perhaps the last line, you might wonder what's going on here at 0.84 for hippocampus DD1. And we took a closer look at that one to see why they were slightly more different. And the reason why they were different is because Cayman had some spatial footprints that were very weird. There were inconsistencies in the footprints that were identified with Cayman, and that led to this difference between what we're getting in IDPS and Cayman. And
so at the beginning, we were really concerned about matching Cayman's outputs as closely as possible, and that's what we did for like 90% of the development. Once we were really confident that ours was good, that's where we started to then tinker and see where we could improve. And I think we're pretty confident after digging in pretty carefully to these data sets that the differences that we do see we feel like those are actually places where we've made improvements over the spatial footprints and temporal traces, rather than places where we're failing to identify cells that came in picked up. Of course, not saying that we never miss a cell. There are a couple here and there, but I think overall these differences are driven by cleaner spatial footprints that we're getting, which might have to do, we haven't tested this rigorously, but might have to do with this improved way of merging patches.
Yeah. And with that, I'll turn it over to Shay to show you guys yet another feature that's available in IDPS 1.6.
Okay, so that was the biggest part. Obviously, I have two more small things to show you guys before we go on. A couple minutes. Is there more questions about CNMFE that you guys would like to discuss, or bring up something that we can go into more detail another time if there's anything that wasn't clear here?
I mean, just to say congrats, because I think that would be like really good for our customers. I mean, they're expecting that since you know, a lot, and I think it's yeah, it's great.
Thank you. Yeah, it's been a really rewarding project for us to work on, I think, and I really feel like Bruno's done a great job of taking a complicated algorithm. This is not a simple algorithm, and translating it into a totally different language while maintaining the performance. So
just a curiosity, are you going to publish this?
Yeah, that's a good question. So we're in talks with Liam Paninsky to show. We have some criticisms of Cayman after taking a really deep dive. We haven't really gone into it today, but there are, we think, some mistakes that we found in Cayman after digging in really, really deep. And we're writing that up now as something to talk to Liam Paninsky about, who obviously was the group that CNMFE came out of. We want to get his take on it, whether or not he already understands those differences, he's already known about them, if he's interested in them. And then we want to approach potentially collaborating with him on a paper where we compare and contrast the different CNMFE algorithms. So that's our current understanding. We haven't really thought about just publishing ourselves, because we really did implement this from Cayman, right? We don't want to, take total intellectual responsibility for this. We didn't come up with it ourselves. We were inspired and sort of built off of the progress that they had already made. So we'd rather do that in collaboration with them if possible, to recognize that contribution.
Thanks.
Cool. Okay, well, the next part, thanks Bruno very much for going through that. That was, I think, super informative. I hope you guys, that was helpful for you guys as well to get context for what's in this algorithm and how it works. So I'm going to talk about two more modules in IDPS 1.6 pretty briefly here. The first one is deconvolved traces. And so this is actually a module that we did because it's something that we had to build for CNMFE. So part of CNMFE, part of the way that it does that fitting of the temporal traces, how it estimates that temporal trace, is that it tries to fit an autoregressive model to the time series data and deconvolve the trace into underlying spikes, and then the true calcium concentration that is being buffered by the GCamp according to GCamp's on and off rates of binding affinities to calcium, right? That's what's kind of really going on that we're trying to measure. And then we have a bunch of noise around that signal that we're trying to estimate and subtract off. And so we thought that offering deconvolved traces as its own module would be helpful, in that now you can try and denoise any traces that you get, whether it be from CNMFE or PCI-CA or manual ROIs. So you can try to denoise those traces and estimate the underlying spike train that best explains that noisy data that you got from the movie. Okay, so use this tool to estimate the underlying spikes and the biosensor kinetics, i.e. the GCamp activity, which is reflecting the calcium concentration from noisy calcium imaging fluorescent time series data. So the input to this is going to be a cell set, a dynamic cell set. Doesn't matter how you got that cell set from any of the three methods. And it's going to output two things. It's going to output an event set, which is the spikes that it estimated, and then a cell set, which contains the denoised traces, which is basically the spikes convolved with the time with the time kinetics that it estimated that the calcium buffer had from the data. Okay, So you can kind of see that here. This is a figure I pulled from Friedrich et al. 2018, which is, they published this OASIS algorithm, which we re-implemented for this purpose. So here you can see like your Y is your noisy calcium data that you would collect at your individual time points. And then what it's doing is it's fitting a series of spikes and then convolving those spikes using specific decay kinetics to then get your denoise trace in blue and your underlying spike train in S here, or orange. Does that general concept make sense to everyone? Deconvolution using an autoregressive model. So here's what it looks like in the GUI. We'll go there for a second. You access it under additional tools. You can choose whether or not you want to save both the denoise traces and the inferred spikes, or one or the other. And then there's a couple different parameters you got to choose. So the most important one is the model order. This, in an autoregressive model, autoregressive means that you're using previous time points to predict a future time point. And the model order is saying how many previous time points do you use to predict the future time point. So the simplest way is to use an order 1 model, which just uses the previous time point to predict the next one. Another one is order 2, which uses the previous 2. We have both 1 and 2 implemented right now. 1 is implemented for OASIS and SCS, these 2 different implementations we have, but 2 is currently only with SCS. Now, why do you use 1 or 2? Well, generally it depends on the frame rate that you have. So if you're about 10 hertz or lower, an order 1 model will work great. If you're more like 20 to 30 hertz, you're going to want to use an order 2 model. That'll do a better job of deconvolving the traces. We'll try and for future work implement the order 2 model with OASIS. That'll be much faster. OASIS is much faster than SCS. That's because we had a really talented co-op last semester named Machine, who was actually able to speed up the implementation of OASIS by more than 10-fold over what they published in this paper in PLOS Biology, which was really cool. So those are the most important parameters. Obviously, you can choose whether your cell statuses you want to accept, and then you can also choose your spike SNR threshold. So this will then only write spikes in your resulting spike set that has an SNR threshold, SNR above that threshold, if you want to take out low SNR spikes. And then you have a couple advanced features here, which for the sake of time right now, I'm not going to go into in detail, but the noise range is between 0 and 1. That's going to affect how your noise is estimated, which then affects what your signal to noise ratio is for your spikes, as well as your noise method, again, estimating that noise. The number of lags and the fudge factor is going to affect how you estimate the decay kinetics of the calcium indicator. So that's going to basically, in the algorithm, it's trying to infer what the exponential decay kinetics are, and that's determined by the number of lags and the fudge factor. Again, we have these 2 different algorithms. One is SCS, which is a general package for solving these kinds of problems that was already written in C++. So we use that. It's slow, it's pretty slow. And so we were inspired by the OASIS algorithm, which was written in Python. And we re-implemented the OASIS algorithm in C++ for this reason. And we're able to speed it up quite substantially. So if we go take a look at what that looks like in the data. So here I have my matched data set from our multicolor registration. That's as good a data set as any to run deconvolved traces on. So now if I'm being blocked by my Zoom controls. So now if I go to additional tools, I can see deconvolved traces is active. I click that. I have my traces, spikes, my model order. I'm not quite sure what frame rate this was taken at, so I'm going to try a model order 1 and see how it looks like. So I'll click apply. Now underneath matched, we have 2 cell sets. Now this is a bit of a new concept in IDPS. Normally, I think this is the first time that you've ever seen a cell set underneath another cell set. And that's because we're maintaining the convention that data is loaded underneath another piece of data when it was derived from that data. And in this case, the denoised traces and the spikes were truly derived from the raw cell set. And so we're loading them underneath that to signify where this data came from, okay? So Here's the denoise traces. Now you can see right away that they are denoised, but these are still looking fairly noisy here. So I wonder if I use an order 2 model, if this would look a little bit better. And then these are the underlying spikes that made that up. Now notice that we're calling them spikes and not calcium events. In detect events, what that's really trying to do is detect single calcium events. This is different. This is trying to detect the underlying spike pattern that gave rise to those calcium transients. It's a subtle difference, but it's a bit of a different way that you interpret these values. Basically, the calcium events are going to be some sort of subset of this spike train that we're trying to estimate. I don't know how long it would take to run an order 2 model. We can try now. I'll try really fast, but if it takes too much longer, then I'll let it go. Looks like it might not take too long. Okay, didn't make too much of a difference here, actually. So this might be the limit, and it might also just be because this is truly bad data, and so it's not able to model this data very well with an autoregressive model, and so we're not recovering great clean spikes. Up here, you can see these guys are much cleaner, and those probably represent higher quality cells. Okay, so I'm just gonna, are there any questions there before I move on? I have 1 more minute, which I'm gonna use for one more thing.
So I have just a quick question. Is it possible to visualize them together? Just how many spikes within, like we used to do with the events, for example, on the
Yeah, so because we're maintaining the same convention, under match, now you'll be able to put spikes on. And so you can see the spikes that were estimated on the raw data. If you want to see the spikes on the denoised data, you just need to re-import the spikes underneath the denoised data, and then you'll be able to view that, okay?
Okay, thanks.
Good question. Okay, the very final thing that I'll do in the last minute, and this is not really that, it shouldn't be that take very long. So I'm just gonna get a movie or a movie like this. So if we go to identify cells in PCI-ICA, you'll see that this looks a little bit different. For a number of ICs, now you have a selection of whether you want to choose auto or manual. Manual is going to be the same thing that you saw before. So that just means that you estimate the number of cells that are in there, and then of course add some sort of factor like 15 or 20% more than that, which is what you should use for the number of ICs. We've implemented a way to automatically detect that using a blob detection algorithm on a max projection image that we've benchmarked against 50 data sets or so, and found has pretty consistent and accurate results for the IC parameters that should be used. It's not always perfect, but it does a pretty good job most of the time. And so for that, you can select auto here, and all you need to do is enter in the average cell diameter. So again, here, if I wanted to do that, I could draw a line here. It's a little bit hard to see on this movie, obviously. And so one thing I might want to do before doing that is like run a project movie or something, and then that would make it easier to get the average cell diameter of say 6 over here, and then use that as an input to PCI-ICA, to run PCI-ICA, and then get a cell set from that. So that's it.